Okay, so that was the discussion of correlation, covariance, and correlation coefficient when we have two random variables. If we have a random vector with components more than two, then we can define what we call the correlation matrix and the covariance matrix. Of course, correlation is defined with respect to two random variables. So here, to represent the correlation between each possible pair in a random vector, we define this matrix, which includes all correlations of all pairs. So x1 by itself here is the second moment of x1, x1, x2, x1, x3, and so on up to x1, xn. And here I would have x2, x1, x2, second moment, x2, x3, and so on up to x2, xn, and so on. You get the idea. Okay. And obviously, one thing you have to notice here is expected value x1, x2, or the correlation is, well, it's equal to this. So I change the order, it doesn't change. So this matrix here is symmetrical. So this here is equal to this here. This third one here would be equal to this third one here. This xn x1 is equal to x1 xn, and so on. This one to this one. Okay? Sorry, this one. So this matrix is a symmetric matrix, and the components are the correlation between each pair. So this is symmetrical, important property. Of course, special cases, when n is equal to 1, what you get is just the second moment. If n is equal to 2, on the diagonals, you get the second moments, and on the off diagonals, you have the correlation here. Of course, these two are equal to each other. Okay. Similarly, we define the covariance matrix, okay, defined in this way. And now, instead of correlations, in this matrix, we have covariances. And when x1 and x2 are the same, you get variance of x1. So on the diagonal, you see, this shouldn't be a square here, sorry about that. On the diagonal, you see variances. And of the off diagonals, you see the covariances, x1, x2, x1, x3, etc., up to x1, xn in the first row, and so on. And of course, again, this is a symmetrical matrix because covariance x1, x2 would be equal to covariance x2, x1. Okay. And another observation is this. If you remember, the covariance between x and y was equal to the correlation minus product of the means. And this is the generalization. The covariance matrix is equal to the correlation matrix minus the mean vector multiplied by itself. But you see, this is what we call an outer product. Well, because the mean vector is a vector, it's a column vector. So you say you have a column vector here, and its transpose here is a row vector. When you multiply them, you get a matrix. Okay. And this expression is, of course, a generalization, sort of a generalization of these identities we know. The variance is second moment minus the square of the first moment, and covariance equals correlation minus the second moment. Sorry, the product of the means.